Thanks a lot. Let me also thank the organizers for the invitation. It's really great to be here. Really fantastic workshop, fantastic week. So I would like to tell you about some of the progress in simulating 3D quantum systems with iPEPS. So both isotropic systems in 3D and then also 2D layered systems. So I mean, so strongly anisotropic 3D systems. And then I will also tell you about applications to strontium copper borate, so where each layer is described by the Shastry-Sutherland model. So the most important person involved in all these developments is Patrick Flower, who's going to finish his PhD soon. Okay, so I guess in this audience, I don't need to motivate too much, right? So I guess everyone agrees that tensor networks have been enormously successful for many problems. I mean, with matrix product states, there's countless many examples, but also with 2D tensor networks, there's really a very nice growing number of applications. So really, to challenging problems, including frustrated spin systems, SUN systems, TJ Hubbard models, and more, right? So this is just like a selection of some of the works over the past 10 years. So this is not a complete list, but just to give you the impression of this really strongly increasing number of applications and also an increasing number of groups who make use of these tools in 2D. So in view of this progress, there's the natural question if we can also use this for 3D quantum systems. Now, of course, writing down the iPEPS ansatz in 3D is simple, but the main challenge is really here, how are we going to contract these 3D tensor networks? Now, there have already been quite a few works, especially in the context of 3D classical partition functions, but then also in 2+1D. So think about the 2D quantum state where you do imaginary time evolution. This in the end also boils down in contracting a 3D tensor network. So for example, we have higher order TRG in 3D that was introduced in this paper here. There's generalizations of the corner transfer matrix method to 3D. There's several approaches based on the boundary iPEPS. So where you start from some initial guess for a boundary iPEPS, and then you start applying PEPO layers to this iPEPS boundary until you reach convergence. So there's several works here, and there's also some other types of approaches here. Now, our goal was not to come up with the most accurate way to contract 3D tensor networks, but to come up with practical algorithms that come with a good trade-off between accuracy and computational complexity. Right? And I will tell you about 3 different approaches in this talk. So let me just give you a very quick overview of these approaches, and then we'll go in much more detail during the talk. So the first idea is just instead of doing a full contraction of the 3D tensor network, that we evaluate things on clusters of tensors. So as an approximate contraction when we want to compute, for example, local expectation values. Right? And we will consider clusters which are not too large, so this can be easily contracted, and it's also computationally not too expensive. So this comes with a limited accuracy, but it can be something useful to get some quick results, and I will show you some benchmarks here for the 3D Bose-Hubbard model later. Then I will also tell you about a full 3D contraction approach, which we call the SU plus CTM approach, so simple update plus corner transfer matrix. It's based on a boundary iPEPS, and the main idea is that we split the PEPO into a sequence of 2-body gates that we then absorb into the boundary iPEPS, where we make use of simple update truncation. And then in the end, we contract then the resulting quasi-2D tensor network. So we'll see this comes with a good accuracy and also a good convergence behavior, and in the end also with a tractable computational cost. Then I'll also tell you about an approach that it's designed for layered systems, so which are strongly anisotropic, so we have just weakly coupled layers. And what we do in this approach is that we try to do an effective decoupling of the layers, such that in the end we can use 2D contraction algorithms to contract these decoupled layers, and we keep some connections in between. So we will see this has a good accuracy for anisotropic systems and definitely also with a lower computational cost than these full 3D contraction algorithms. I will tell you more details about all these methods and then show you benchmarks and applications. But to get there, I will introduce somehow the main concepts that we borrow also from the 2D algorithms. So that, it's about contraction of 2D iPEPS, the coordinate transfer matrix method, and then I will also review the main ideas of the imaginary time evolution algorithm with a simple update, cluster update, and full update truncation. These will all play a role then in 3D. Okay, so I guess most of you have seen this, how to contract a PEPS in 2D. So here we have the ket of a PEPS of a 3x3 system. Here we have the bra, and then we can, push the two layers together, and we can combine bra and ket tensors into one. So this results in this, oops, the button is somehow a bit stuck here. This results in this square lattice tensor network here with double lines of bond dimension d that we can combine into one. So to compute the norm of a PEPS, we have to contract such a square lattice network with a bond dimension d squared, right? And this cannot be done efficiently in an exact way. So there's various ways how to do this in an approximate way. And the method we will use here for the 3D approaches is the coordinate transfer matrix method. Okay, so let me just give you the main idea here. So we have this infinite 2D network that we want to contract. And imagine now we want to evaluate something here in the middle of the system. Now the coordinate transfer matrix approximates all of the tensor networks surrounding the central site by these environment tensors here. So consisting of 4 coordinate tensors and 4 edge tensors. So this coordinate tensor C1 here represents all the upper left part of the system, and this edge tensor here would correspond to this infinite column here, and so on. Right, and then the accuracy of this approximate contraction is controlled by this boundary dimension chi here. Now the CTM approach is one way how to get these environment tensors in an iterative fashion. So let me show you here the main idea. So it's based on letting the system grow in all directions. So let me show you here how you can grow it on the left side of the system. So for this, we first start with initial guess for the boundary, and then we introduce a new column of tensors, so just a copy of T1A and T3 that we then absorb on the left side of the system. So we have then new tensors here on the left side with an enlarged bond dimension, and then the last step, we renormalize this large bond dimension down to a smaller one, so to the original bond dimension chi here. Right, so this is called a left move. So we have let the system grow on the left side, and then you can also do a right move, a top move, and a down move, and then you can repeat this over and over again until you have reached convergence. Okay, so this can also be easily generalized to arbitrary unit cell sizes. Okay, so that's the CTM method, and then now let me also yeah, please. The conditioning, or you mean the renormalization? Indeed, so there's different ways how to do these renormalizations here. There's different proposals. And so I'm not going to the details here, but essentially what we usually do is to split the system and then essentially see it as a matrix product state that you want to compress in the middle. So in the end, you just bring it into canonical form in the middle and then compute the corresponding projectors. So that's the main idea that we use here. But there's, in principle, there's different ways how you can do it, because in the end, it's connected around. So it's in the end actually a periodic problem. Yeah. Okay, so let me briefly go over the main ideas of the imaginary time evolution, which I guess most of you know, right? So the idea is to apply the exponential of minus beta h to some initial states, and this projects you onto the ground state for beta going to infinity. And then we typically use a Trotter-Suzuki decomposition. So where we bring this into a product of these exponential with a small time step tau. And for simplicity, we just consider here nearest neighbor terms. So in one dimension, if we consider an infinite matrix product state, so in this special form here with the weights on the bonds, then what we do is every time when we apply such a two-body gate, we include the weights, the neighboring weights here, which brings the infinite MPS into canonical form here, and then we use an SVD to split these things apart again and keep the D largest single values, right? So this is the well-known ITBD algorithm. Now in 2D, we want to do the same thing. So we have a sequence of two-body operators that we apply to our PEPS or iPEPS, and then every time we also need to truncate back to the original bond dimension again. Now, the problem is now if you do an SVD type update, this is no longer optimal because of the loops in the tensor network. So whenever you consider a bond in your tensor network and you split it, you don't split your network into two parts. So you cannot think of this as being a Schmittig opposition, which in the end is the reason. So there's no canonical form, which is the reason in the end why this SVD type local update is not optimal. But you can still use it, and it gives quite reasonable results, for example, for energies. And its computation also very cheap, so it's called the simple update. So it's local and really works like ITBD in one dimension. But then it has also limitations, so often you would see that order parameters get overestimated using this approach. So if you want to have a more accurate truncation, one can use this full update method, which in the end takes the full wave function into account if you do a local truncation, right? So this is optimal for local truncation, but also more expensive because you need to do a full contraction of your 2D tensor network. And there's also this fast full update in the end, which just based on trying to recycle as much as possible from the previous environment to speed up the calculation. Then there's also another approach called cluster update, which kind of is in between these two. So instead of doing a full contraction, you just consider a cluster of sites for the truncation. So let me just show you these approaches in a bit more detail. So here's the simple update in 2D. So we also work like in ITBD in one dimension. We work with a representation with weights on the bonds. And then it really works very similarly as in 1D. So when we apply a two-body gate, we include all weights on the bonds, and then we use an SVD to split this tensor apart again, and in the end, we just extract the neighboring weights again, right? Again, unlike in 1D, this does not bring the PEPS into a canonical form or into a Schmittig composition, but it's only kind of, it just gives you approximately some efficient or some effective environment. And for the full update, what we do is to really contract the entire 2D tensor network to compute this environment, so surrounding these two tensors A and B. So here is our imaginary time evolution wave function psi tilde, and then we try to approximate it by a new PEPS, so new tensors A prime and B prime, with a bond dimension D in between. So what we do in the end is to minimize the norm difference between the untruncated and truncated wave function, which can be done in an iterative way or also using a conjugate gradient or Newton scheme. Okay, so, wow, this button is somehow tricky. Here we go again. So again, this is more expensive because every time you do a local truncation, you have to compute this environment, but it's then really also an optimal local truncation. Now the cluster update is similar, just that instead of doing a full contraction to compute this environment, you approximate the environment by a cluster of tensors, right? Also including the weights around the boundary as kind of an effective environment surrounding these clusters. Okay, so this has been used in different papers already, and let me also mention that instead of using such a cluster approach for, in the context of an imaginary time evolution, you can also use it to approximately evaluate a local expectation value. And that's the approach that we also tried in 3D. So let me move to that part now. So we used clusters to approximate local expectation values. So here are the smallest possible clusters here, just 1 times 1 times 1, and here just 2 tensors in 3D. So where we also include the neighboring weights. So this is computationally very cheap to contract this, but it also has a very low accuracy. So that's not, it's not very useful. So we typically considered clusters which are larger, as shown here. So this is a large cluster here, which gives quite okayish results, but it's also quite expensive to contract. And then this cluster here, so just a 2 to the cube, is computationally reasonably cheap and can be used to get kind of a rough estimate of local expectation values. Okay, so that's the idea of these cluster evaluations. And now let me move on to this full 3D contraction algorithm, so the SU plus CTM approach. So it's a boundary iPEPS approach. So we start from some initial iPEPS boundary here, and then the goal is to absorb layers, so PEPO layers, onto this boundary repeatedly, and then always truncate down to some bond dimension. So here we call it chi-b. This is the bond dimension of the boundary iPEPS. And now the scheme we are using is the following. So we take here the ket of this PEPO and then split it apart into small pieces using a sequence of SVDs. So as shown here, so this gives us this string of tensors here. So this we do for the ket and also for the bra. And then we use 2 different splittings for the tensors on 2 different sublattices, such that if we align them, you see we have these 2-body operators appearing here in this placket network. And then the idea is to always absorb such 2-body operators into the boundary iPEPS. So here we have this. So this would be 2 tensors from the boundary iPEPS, now also with the weights on the bonds. We do this on the ket and the bra level, and then we use a simple update truncation then to approximate the resulting boundary iPEPS. Okay, so we do this for all these 2-body operators, and we do this repeatedly until we have reached convergence of this boundary iPEPS. Now we do this from the top and then also from the bottom. So this results then in a 3-layer network, so with a bottom and top boundary iPEPS and the middle PEPO layer. And then we contract this resulting 3-layer network using the standard corner transfer matrix method, right? So then we have here these environments here, which have, so here a bond dimension chi-b, so that's from the boundary iPEPS. Then the bond dimension D connects here to the PEPO layer, and then we call the bond dimension of the CTM, we call chi-c here, right? And that's then the resulting computational cost, which is a combination of these 3 bond dimensions. So we have benchmarked this approach first for the 3D Heisenberg model, and now to optimize the tensors, we have just used the simple update approach in 3D, which is just a very simple generalization from 2D. And then, oh wow, maybe I should switch this. Huh? It's going to happen more often again. So I have another one here. Sorry? Okay, okay. Well, let me try again then, or just push less hard, I don't know. Okay, anyway, let me try. Okay, so we looked at the convergence in all these bond dimensions. So here I show you the convergence in this bond dimension of the CTM. So you see here we obtain a good convergence in the energy. And well, the larger the bond dimension of the PEPS or the boundary bond dimension, then we also need to go to larger chi-c. But overall, we find here a good convergence with a small error here compared to the changes in D here. Here I show you the convergence as a function of chi b, so that's the bond dimension of the boundary iPEPS. And also here it converges quite rapidly. So for D equals 2, we essentially are converged for bond dimension 4. That's for D3. So here we need maybe 5, and here we need around 6 as a bond dimension of the boundary PEPU. And in this plot, you also see some results from these cluster contractions. So here are the smallest clusters, so just with 2 sides, and you see they're really far off, so they're not very useful. Here, the square here is the 3 times 3 times 4 cluster for bond dimension 2, which is reasonably accurate here. But that's also quite expensive, so we can also do it for only do it for D equals 2. And then the triangles here are from this 2 times 2 times 2 cluster here. So you see they're off, but definitely better than the smallest cluster here. So I mean, you can see it maybe as sort of a rough estimate of what you should obtain. Okay. Yeah, maybe I, indeed. So here we go. Let's see if this works better. Okay, now here I show you a comparison with higher order TRG. So higher order TNG, you have a question? This one here? Yes, indeed, yes. So it's not very far off here, but yes. I mean, the accuracy is not really controlled, but at least you can take it as a rough estimate, let's say. Yeah, yes, please. Yeah, I think it's definitely on the scale is larger than here. Maybe I can show you I'll come to that. Maybe we can see it in another plot actually. Yes, indeed, that's this here. So we used an imaginary time evolution based on the simple update in 3D. So that's the optimization we used. So that's a simple optimization, but in the end we were interested in benchmarking the contraction first of all. Yeah. Yes, please. Yeah, so it's the computational cost in the end is kind of a complicated function of all these 3 bond dimensions. But let's say to compute this benchmark data, right? So I mean, I guess the most expensive calculation is maybe of the order of a day or so. So that's yeah. Okay. So now here I just wanted to show you comparison with higher order TRG. So you see, with higher order TRG, which is this coarse graining technique in 3D, we found that the convergence behavior is very irregular. So it seems to, here for the magnetization, it seems to tend to similar values, but it makes it difficult to know at what point it's actually converged, right? So we found that in terms of convergence, our approach seems to be more systematic. Okay, and here I show, yes, please. Indeed, for the 3D, exactly, for the 3D, to contract the 3D network of the optimized tensors, yes, indeed. Okay, and here I show you some attempts to extrapolate where we made use of this idea of finite correlation length scaling. So where the idea is that instead of doing finite size scaling, we compute an effective correlation length for each value of D, and then we use this as a quantity to make extrapolations. And now you see here, this is the quantum Monte Carlo data here. So for different system sizes. So that connects then to your question, what the finite size effects are. And here is our iPEPS data here. And for the energy, we obtain quite a good result here. For the magnetization, this extrapolates to a higher value, so it's 2% off, but this is most likely due to the fact that we have used simple update optimization here, right? So I think we can really improve that also by using more accurate optimization techniques. Okay, and then we also did benchmarks for the 3D Bose-Hubbard model. So here you have the superfluid phase for large T over U, and here are the mod insulating phases, so the n equals 1 mod lobe and n equals 2 mod lobe. And here I show you comparison with quantum Monte Carlo in green, and then also with the bosonic DMFT. Okay, so first observation is that for d equals 2, we can already obtain a systematic improvement over the mean field result, so shown here by the dashed line. And then if we go to d equals 3, we are actually already quite close to the quantum Monte Carlo result, and also kind of better than this bosonic DMFT calculation. Now, the squares here are the results obtained with this 2 times 2 times 2 cluster, which are actually quite close to the full 3D contraction shown by the star here, right? So this is an example where, the cluster contraction is not very accurate, but it seems to be quite close to the full contraction, so we can use it as a quick way how to obtain here this phase diagram, right? Okay, all right, so that's these things. So now let me move on to the layered approach. So the motivation here is that, there's many systems in nature which are, of course, strongly anisotropic, and the best known example here are the cuprate high TC superconductors, right? Essentially, people believe that all the essential physics happens within the 2D oxygen planes, but still there's still interlayer hopping and interactions between these layers, which can have an effect on the physics, right? And probably the best example is that, of course, in the material, there's a finite temperature phase transition into the nil phase, which, if you take just a plain 2D model, is at 0 temperature due to the Mermin-Wagner theorem, right? So an interlayer coupling naturally leads to a finite nil transition temperature. Another point here is that if you go to the doped case, there's a very strong competition between different low energy states. And now adding an interlayer coupling, even if it's small, could also have some significant effect on this competition of low energy states. And of course, there's many examples also from frustrated magnetism, for example, Herbert-Smithite, so the Kagome compound that also has a finite interlayer coupling, or strontium copper borate, or there's many other examples. So, for these type of problems, we start from an anisotropic iPEPS ansatz, so where we use a large intraplane bond dimension dxy compared to the interplane bond dimension dz. Right? So in the most extreme case, we would use just a dz equals to 1, which would correspond to a product of iPEPS layers. Right? And if the interlayer interaction is small, this is actually already a useful ansatz to explore these systems. Now, how do we contract this network? Now, if we take the dz equals 1, then of course the contraction is simple because it just boils down in contracting independent 2D layers. Now for dz larger than 1, we do the following. So imagine if we want to compute a local expectation value in the middle here, what we do is to effectively decouple these layers away from the middle, and we do this by doing a full update truncation from dz, from a finite dz onto dz1, right? So we effectively decouple the layers, but we keep the connections in the middle. And then we can use the standard 2D approaches to contract the networks around the middle. So this gives us then, this one-dimensional column of the layers. And then eventually this we can easily contract simply by replacing it by the leading eigenvectors from this transfer matrix here. Right, so in the end, this allows us to recycle approaches from 2D, But in the end, we can still keep the most dominant interlayer correlations beyond the mean field level by keeping these connections in the middle. And here I just showed you one connection, but of course we could also keep more than one connections in the middle. And we call this the layered corner transfer matrix method. Okay, so here I show you the example of, for two-side observables, we use such two connections here. Or Patrick has also played around with schemes where he also kept a finite connection in the CTM environment here so that we have effectively 5 connections here in this example. But these are computationally more expensive, so the most results I'm going to show you are here based on these fewer connections. Okay, so we have benchmarked this for the 3D anisotropic Heisenberg model. So here for this coupling ratio of 10%, and compared to here the extrapolated quantum Monte Carlo result. And you see the blue data here is for dz equals 1, and that's already, I mean, it's already quite useful, it's already quite close to the quantum Monte Carlo result, but then you also see if we go to dz 2 or 3, we can substantially improve this result. And then we also compare this to the full 3D contraction in black here, where we obtain a good agreement. So here I show you some data for different coupling ratios here. So here we have a ratio of 5%. Now here you see that if you compare the dz1 and dz2, they're essentially on top of each other, right? So already a mean field type ansatz, a product state ansatz between PEPS layers already gives you actually quite good result. And then you see here, as we increase the coupling ratio, this difference between dz1 and dz2 starts growing. So with growing interlayer interaction, we should then also increase the interlayer bond dimension. So here's some additional data for the magnetization. So here we did not find a strong dependence on dz here. And these are the spin-spin, nearest neighbor spin-spin correlations. So these are in the plane, where we obtain high accuracy. And then the out-of-plane spin-spin correlations, they're a bit less accurate, but you also see here that they're approaching the quantum Monte Carlo result if we increase the dz. Then we also tried out different optimization approaches here. So the data I've shown you before was just obtained with a full update optimization, but here we also tried with a simple update optimization or cluster update optimization. So the cluster update already gives similar energies as the full update, but it's a bit less accurate here on the order parameter. Let me check time. So, okay, so this was the benchmarks, and now we also currently applying this idea to the Shastry-Sutherland model with interlayer coupling. So let me just give you a brief introduction here. So the Shastry-Sutherland model is, can be seen as a square lattice Heisenberg model with this additional diagonal couplings here, or that's another way how to draw the lattice, so a lattice of coupled dimers. And this is really a very nice realization in strontium copper borate. So this is a layered system where the copper ions here carry the spin 1/2 and where the same lattice is realized. Okay, so here's the phase diagram as a function of j prime over j. So in this limit here, you have a dimer phase, so just the product of singlets. In the other limit, you have a nil phase. And in between, there's a placket phase. So that's a non-magnetic phase which breaks translational symmetry. More recently, there have also been new calculations suggesting that there could be a narrow spin liquid phase here in between, but I will not go into the details of these new calculations. So that's still one additional possibility. Now, strontium copper borate lies in the dimer phase, but relatively close to this placket phase here. And I mean, one of the fascinating properties of the material is you see once you put it in a finite magnetic field, it exhibits a very rich variety of appearance of magnetization plateaus. So there have been many works on the theory and the experimental side to identify these magnetization plateaus. And in particular, it was one of the earlier successes of iPEPS to predict the structure that are realized here, which can be understood in terms of crystals of triplet bound states. So these type of spin patterns here, these are bound states of triplets which form these crystal structures here. Okay, now another fascinating feature of this compound is that you can put it under pressure and then effectively change the ratio J prime over J. So that was achieved already in a series of experiments, in particular in this paper here where they performed specific heat measurements. And what they found is essentially that, here they're in the dimer phase, and then down here they found another feature in the specific heat, a smaller peak, which they identified with the placket phase, and then here eventually there's the antiferromagnetic phase. Now, if you look now at the extent of the placket phase predicted from experiments and convert pressure into J prime over J, one finds that the prediction from experiments has a value here which is much smaller than the prediction from theory. Okay, now the natural way to understand this discrepancy is due to the lack of interlayer coupling in the model, which is neglected in the standard 2D Shastry-Sutherland model. And this was already discussed in this paper here by Koga in 2000. So he considered now the model with an interlayer coupling, so J double prime, and used series expansion to compute this phase diagram. So you see here the placket phase is down here, and it shrinks very rapidly when you increase J double prime. And so the antiferromagnetic phase becomes favored over the placket phase with increasing J prime. And the reason is because you can take the antiferromagnetic state and stack it such that the antiferromagnetic order is not frustrated. So if you add an interlayer coupling, this will lower the total energy. This is in contrast to the placket phase, where the interlayer coupling has only a small effect. 10 minutes, okay, great. So there are a certain number of predictions what the value of J double prime is. So from fits to the magnetic susceptibility, so values between 0.09 and 0.21 were predicted, whereas here from this ab initio calculation, it was a smaller value here. So in the end, there's still no consensus yet on this value. So we used now this layered iPEPS approach to get insights into this problem and computed the phase diagram. So here I show you the phase diagram for dxy equals to 5 and then different values of dz. So you see here, this is kind of the product of iPEPS, so the blue one. And then going to dz2 and 3, we obtain these lines here. So they don't change much anymore as we increase it. And then here I show you the phase diagram now for fixed dz equals 2 for different bond dimensions dxy. So this goes slightly up. So with dz, it goes slightly down. And also here, the phase boundary does not shift much anymore. So we think we already have quite a good estimate of the phase boundary here. And now we can take the prediction from experiments and then check what would this mean for the value of J double prime, right? And our estimate we obtain here would then correspond to 0.03, which is also kind of close to the ab initio prediction. Okay, so this is just the first application, so still work in progress, of this layered iPEPS approach. And we believe this is going to be useful also for other type of layered systems. All right, so in the remaining few minutes, I would just like to highlight a few other recent applications to strontium copper borate, so using just the standard 2D iPEPS. So the first one directly relates to this, to this here, to the specific heat. So we also had a collaboration with the group of Henrik Rönhoff, where we looked at the evolution of the specific heat under pressure and as a function of temperature. So here we used a finite PEPS approach to compute the specific heat. So here you see the experimental data where they found that the maximum of the specific heat is shifted to lower temperature as a function of pressure and then becomes extremely sharp here. And we found with iPEPS at finite temperature, we found a very similar behavior here. And in the end, what happens here, so this is, what we found here is that this corresponds to a critical point at finite temperature, right? So here you have, you have a phase transition of dimer between dimer and placket phase, which is a first order, and this first order phase transition extends to finite temperature and ends here in this critical point. So this is very similar to the critical point that you can find in the phase diagram of water. So we called it a quantum magnetic analog to the critical point of water, which was then published in this paper here. So well, also Frederick Mila involved and several other people from theory that worked on this project. Yes? Sorry? So this was a finite temperature iPEPS approach, so representing directly a finite density operator at finite temperature. So this is a bit of a teaser of what we're going to hear, I think, in Piotr Czarnik's talk later, so doing finite temperature iPEPS. I just wanted to flash this as one of the things in the end, also to, if someone is interested to hear more details, that will be happy to discuss. So let me jump over this. And then, so this is a collaboration together with Piotr, Jacek Jarmaga, and Marek Rams, where we looked at the finite temperature transition into the 1/2 plateau. This is only a teaser because I'm sure Piotr is going to tell us about this in full detail. Then I just wanted to mention this other recent collaboration with the experimental group of Sarah Haravifard, where we looked at strontium copper borate under extreme conditions of field and pressure and trying to get an understanding of the anomalies they found in the experiment, so which they detect phase boundaries, and then compare this to the iPEPS phase diagram of the material, so as a function of pressure and magnetic field. And here we found a very good agreement between experiments and iPEPS calculations for the locations of the phase boundary. And we also discovered new type of plateau phases here with new types of spin patterns and also new types of supersolid phases. Okay, and then the last work which I wanted to mention is the also collaboration with the different experimental groups, where they managed for the first time to reach the saturation field, so going to 150 Tesla, which is above the saturation of the sample. And here we also did comparisons with iPEPS. So let me see here. So in the end, we got a good understanding of these new anomalies which appear in experiments. So in particular, the saturation field we found from the iPEPS calculation is in good agreement. And then the other thing I wanted to mention is that we also got insights into the behavior of the sound velocity. So that's the relative change of sound velocity of this particular sound mode here, where in experiments they observed a strong reduction of the sound velocity in the 1/2 plateau. And we managed to relate the change here to the first and second derivative of the magnetic energy. And then by fitting the iPEPS results to these changes here, we managed to get actually quite a good agreement between theory and experiments. So that's just another example showing that iPEPS is a very useful tool to get insights into the physics of this material. I just wanted to flash these things just as a basis maybe to discuss later if someone's interested. But now let me wrap up. So I think, well, simulations of 3D quantum systems are very challenging, but I think they have become within reach. I told you about 3 different contraction approaches that we tested in 3D. So one is based on just contracting clusters, which comes with a limited accuracy, but it's cheap and maybe practical to get first results. I told you about this SU plus CTM approach, which is a systematic full 3D contraction. And then for layered systems, we have explored this layered CTM approach, which is efficient for anisotropic 3D systems. And also I've shown you some application to strontium copper borate. Now, this is not the end of the story, so they should be rather seen as starting points to further developments. Right? So for the cluster contractions, we could go to larger clusters by doing approximate contractions. This approach here, we only tested with a simple update, but it could definitely be improved by going to better optimization algorithms. And then for the LCTM approach, there's also room for improvement. So we could do a better decoupling of the layers by using disentanglers or keeping more interlayer connections or connections within the CTM environment, or also combine it with AD. So that's also possible. Okay, so with this, I would like to thank you for your attention.